Identify the molecular process occurring in the forward reaction. Look at the Lewis structure of the reactant, dinitrogen tetroxide, N2O4. It consists of two symmetric number 2 groups held together by a single nitrogen, N, covalent bond. In the forward reaction, N2O4 gives two number 2. The single N bond is broken to produce two separate number 2 molecules, and no new chemical bonds are formed during this process. Apply the fundamental energetic principle of chemical bonds. A covalent bond is a stable, low-energy state resulting from electrostatic attractions between the nuclei and shared electrons. To disrupt this stable state and separate the atoms, energy must always be absorbed/input from the surroundings. Therefore, bond breaking is always an endothermic process. Energy is required, whereas bond formation is always exothermic. Energy is released. Relate the energy change to the sign of delta H degrees. By thermodynamic convention, when a system absorbs heat/energy from its surroundings, an endothermic process, its enthalpy increases. This is represented by a positive enthalpy change, delta H degrees greater than 0. Cross-reference with experimental observations. This molecular-level reasoning is perfectly consistent with our observation from question 23, where placing the system in an ice bath shifted the equilibrium to the left. A shift toward reactants upon cooling is macroscopic, experimental proof that the forward reaction is indeed endothermic, delta H degrees greater than 0. Select the matching option. Putting these concepts together, delta H degrees greater than 0 because energy is required to break the N bond. This corresponds exactly to option D. The correct answer is option D, delta H standard greater than 0 because energy is required to break the N bond.